Hi, today we're designing something you use almost every day, a URL shortener like TinyURL or Bitly. It sounds simple, but behind that little short link is a surprisingly deep system design challenge, hashing, caching, scaling, and more. So grab your coffee. Let's break it down step by step. Alright, first things first. What exactly is a URL shortener? It's a service that takes a really long link and converts it into a short, shareable alias. Why? Because short links look cleaner on social media, fit easily into tweets, and are easier to track. Marketers love them for analytics. They can see how many people clicked, from where and when. In short, no pun intended, they make links more usable, measurable, and professional. Now, before we jump into architecture, let's talk requirements. Functionally, we need four things. Shorten a long URL. Redirect users from the short one to the original. Support custom aliases. And collect analytics, click counts, and maybe locations. Non-functional requirements are just as important. It has to be highly available, always up. Low latency because nobody wants to wait for a redirect. Scalable to handle billions of links. And durable, meaning we never lose a mapping. These four pairs define the backbone of our system design. Next, let's do a quick scale check. This tells us how big the system needs to be. Suppose we shorten about 4 URLs per second. That's around 600 million URLs over 5 years, only about 60 gigabytes of raw data. Totally manageable. But here's the kicker. Each short link might be clicked 100 times or more, meaning our read-to-write ratio is roughly 1 to 100. Alright, time to build. In the first flow, a user sends a long URL to our server using its shortened post request. The server validates it, generates a unique key, and stores the mapping in our database. The second flow is what users experience every day. They click the short link. Our service receives a GET request with a short URL, finds the matching long URL, and returns a 302 redirect response. Now, let's formalize those APIs. The shortened post API takes a long URL with an optional custom alias and returns the shortened one in 201 created response. If the custom alias passed in the request exists, it returns 400 bad request. The second API is a GET API with the short URL passed as a path parameter. It fetches the original link and returns it in the location header of a 302 redirection response. If missing, it returns 404 not found error response. Pretty simple, but these endpoints power the entire platform. Now comes one of the coolest parts. How do we actually generate those short codes? We have two main strategies. Option 1, hashing. Take the long URL, run a hash function like MD5 or SHA-1, and grab the first few characters. It's compact, but you have to handle collisions. Option 2, base 62 encoding. Give every new URL a sequential ID, 1, 2, 3, and convert it to base 62 characters. It's deterministic, easy to scale, and no collisions. Most real systems go with base 62 for predictability. Okay, our system works. Now let's scale it. Caching layer. We'll use Redis or MEM cached so redirects happen in milliseconds. Database scaling. Add red replicas to spread the load, and shard data by shortcode prefix if writes grow huge. Service decomposition. Split write and read services into microservices. That means each can scale independently and failures are isolated. With these layers, the service can easily handle billions of redirects per day. So that's our complete URL shortener design, from the first request all the way to large-scale infrastructure. It's simple on the surface, but teaches tons of system design fundamentals: data modeling, caching, scaling, and fault tolerance. If you enjoyed this breakdown, smash that like button, subscribe for more system design walkthroughs, and let me know in the comments which system you want to see next. Thanks for watching, and I'll see you in the next one.